Hi everybody, we are back with fluorescence spectroscopy again. So, we have just finished spin chemistry and importance of spin chemistry in fluorescence, means how spin chemistry can be important or spin evolution can be important in deciding the amount of fluorescence quantum yield that is being affected as a result of external externally applied magnetic field. Okay. So, today we are now we are going to start with a little bit of I mean we are going to get you a little idea of how metals can influence fluorescence, and this metal sensing can be done by means of fluorescence spectroscopy, by the use of fluorescence spectroscopy. And also another interesting topic, that is chemiluminescence, that we are also going to discuss today. Okay. Now what is the role of heavy metal with respect to heavy metals or maybe heavy atoms in spectroscopy, especially fluorescence. So, perhaps you recall earlier lectures where we have discussed the issue, that is issue of spin orbit interaction, and also that we also have talked about in our last lecture as well. Now, like suppose you start with, say, naphthalene, and say another example is iodo-naphthalene, 2-iodo-naphthalene. Okay. So, in this case, what do you expect? Expectation is that its fluorescence intensity is considerably reduced as a result of this introduction of iodine, and you can get phosphorescence over here. Phosphorescence in appropriate condition. Now, what is the role of this iodine? That it induces this spin orbit interaction between this singlet and triplet sublevel, singlet and triplet level. So, S1 and this T1 is 0. So, this population is increased a lot as a result of this ISC. So, this is your IA, this is your F fluorescence, and this is your P phosphorescence, and there may be non-radiative processes as well, there can be non-radiative processes as well, but this is your fluorescence, this is your phosphorescence. So, phosphorescence intensity you can expect more in case of iodo-naphthalene than in case of your naphthalene. Okay. Now, talking in line with these observations. Now, suppose we start with some fluorophore, say, okay. So, whose fluorescence we are recording. Now, we study, what we study is we study the effect of heavy metal, you add some heavy metal ion. Okay. So, what is generally observed is that like heavy metals like maybe silver, in some cases maybe mercury you can use, and you can see that whenever those metals are used as the quencher of fluorescence. So, fluorescence is considerably quenched. Okay. considerably quenched as a result of this presence of this heavy metal. So, what is happening that this maybe if the mechanism is dynamic, then maybe this heavy metal is colliding with this excited fluorophore, and of course, this collision must take place within the lifetime of the fluorophore. Okay. So, if the lifetime is such that it is very short lifetime, okay, and if this collision frequency is not that high, then maybe you do not expect to have significant impact or significant effect on the fluorescence by this heavy metal. Or maybe it may so happen that this metal, okay, that this metal is going to form some linkage with some of the functional groups present within the fluorophore molecule, such that maybe more than one fluorophore molecule is coming close to each other, okay, because of this linkage formation. Okay. So, what will happen that in that case maybe two fluorophore molecules, if they are coming close to each other, maybe there may be some stacking effect, there could be some isomer formation or similar effect, or maybe some hydrogen bonding interaction, and as a result of which there may be some shifting of your fluorescence pattern, or maybe some self quenching process, because they are coming close to each other. So, same molecule is quenching another molecule. That means, the effective concentration of this molecule, I mean effective concentration as a result of this process, this this binding process, it is becoming high. I mean because of this binding process, effective concentration near to this first molecule is high. Also effective concentration of the same molecule, self molecule, near to this is also high, because two are coming close to each other. Okay. So, that means heavy atoms or maybe heavy metals or maybe metals can have influence on the fluorescence behavior of the molecule. Maybe if you have say like iron system or iron that is complexed in some organic framework. Okay. Maybe the organic framework does have fluorescence in absence of this metal, but the moment you put this metal, its fluorescence is considerably reduced. Okay. So, fluorescence considerably reduced means there may be some interaction, something happening. Maybe because of this presence of heavy atom, your this fluorescence is basically from singlet state. So, you have this IA, that is excitation, and then you have F. But if this excited state is depopulated, if it is depopulated because of this presence of heavy metal, it is depopulated. Due to then effective population of this excited molecule M star. Okay. This number density is reduced. Number density is reduced means it is giving less fluorescence. Now, how it is reduced? Because of the presence of this M. So, maybe heavy metal means it induces singlet triplet interconversion of M. So, it goes to triplet, M in the triplet, and from triplet it may come down to this ground state via non-radiative deactivation, or maybe some other processes are taking place, so that this overall fluorescence quantum yield is considerably reduced. Okay. So, maybe it is because of the spin orbit interaction, spin orbit coupling mechanism this is happening. Okay. So, heavy metals have influence on this on the behavior of fluorescence behavior of various fluorophores. Now, we are going to give you some examples where these fluorophore molecules, I mean fluorescence spectroscopy. Okay, fluorescence spectroscopy can be used as an important tool in identifying this metal ions. Like there is some selectivity. Suppose you have a fluorophore whose fluorescence behavior okay, fluorescence behavior like your I mean the quantum yield, maybe the fluorescence spectra, that is I mean maybe emission maxima, okay, and also the solvent effect. Suppose if all these are known, now this particular fluorophore molecule, maybe it will be very selective to some ion only, some or maybe a single ion only. Okay. There are examples where you can find interference. You can find interference, but interference could be there, but still important thing is those molecules, I mean those fluorophore molecules are quite selective to some of the ions, means inorganic ions. Okay. So, example could be like calcium 2 plus sensitive fluorophore. Okay, it is called fluo 3. It is a fluorescein based system. Okay, and it's okay. So, it is very sensitive to calcium 2 plus. Okay. So, absorption and fluorescence spectra. So, this is your absorbance spectra, this is your fluorescence spectra. You see that there is a nice mirror image relationship, although in higher energy side some absorption is there, we can ignore that up to this. Okay, up to this there is a nice mirror image relationship. Okay, and there is a little shift, maybe there is a little change in geometry in the excited state maybe, but this nice mirror image relationship is there. And a saturated calcium 2 plus saturated solution at pH 7.2 buffer, this emission spectra is like this. Okay. So, it is a pentammonium salt, it is called the fluo 3 pentammonium salt. So, when you add calcium 2 plus you can expect this type of fluorescence behavior. Okay. So, this is very sensitive to calcium 2 plus, and now it has got a strong fluorescence. This system has got a strong fluorescence, and calcium, in presence of calcium 2 plus, there is some interaction between this one and that one. Okay, and as a result of which some geometrical alteration leading to this fluorescence change. Okay. So, you see, if you think of the emission spectra and excited at this wavelength about 490 like this, somewhere over here, okay, around here. So, when it is excited, you see that with increase of calcium 2 plus concentration, you see it is increasing, its fluorescence intensity is increasing. Okay. So, and there is no, of course, there is no shift, but only this is increasing. So, calcium 2 plus ion may be doing something means some alteration within the molecule, maybe in the solution. It is making some chelate kind of compound that maybe reduces your non-radiative de-excitation, as a result of which it is increasing, its emission intensity is increasing. Okay. So, fluo 3 is a dye which is typically used maybe for the estimation of calcium. So, you can in principle have some this calibration curve. Okay. So, using the calibration curve, you can also find out the free calcium that is present in the system. Okay. So, and the method may can be very accurate as well with a low possibility of errors. Okay. Another example is magnesium sensitive system, magnesium green pentapotassium salt. It is also similar, it is similar type of system, fluorescein like. Okay. This is the fluorescence spectrum magnesium green buffer containing 35 millimolar free magnesium 2 plus. It is similar to fluo 3. You see that this is your emission spectra, this is your absorbance spectra. So, that can be used as a sensor for magnesium 2 plus. So, this chemical this fluorophores are in a sense that if you can find out an appropriate fluorophore, okay, you can also you will be able to detect the particular metal. Point is, or the important point that we should think about is that maybe in some cases there may be interference. Okay, but if there is no such interference, or maybe the interfering ions are present in a lower concentration, then magnesium 2 plus sensitive, this magnesium green, can be a very useful thing. You see, this is excited at 475. You see, it is around this wavelength. It is excited at here. Okay, so excited at here means, just to avoid, why it is excited 475 means just to avoid the overlap between the excitation wavelength and the emission light. So, that is why it means it is started from here. So, that before, much before and much after this, there is a considerable separation between this excitation wavelength and the frequency or the wavelength of light. Okay. The starting point of this emission spectra. Okay. So, you see that up to 35 millimolar of magnesium unit is shown over here, that this is 0.2, 0.41, 0.6, 1, 1.5. So, you see gradually it is increasing. Okay. So, 475 means around 490 the emission has been taken, okay, and up to 650. So, this is very selective to magnesium 2 plus. Okay, this is very selective to magnesium 2 plus. Okay. So, you can in order to know more about this magnesium 2 plus or calcium 2 plus or similar systems, you can search the internet resources. Cadmium 2 plus sensitive, this is another system, cadmium 2 plus sensitive system. This is BTC 5N tetrapotassium salt, it is 5 nitro benzothiazole coumarin. Okay. This is benzothiazole coumarin, okay, and 5 nitro 1 2 3 5 nitro benzothiazole 5 nitro benzothiazole coumarin. Okay. So, this is this is the coumarin based and benzothiazole coumarin based system, and it has got good good fluorescence, and it is very much selective to cadmium. Okay. So, this is the emission spectra excited at 410. If you look at excited at 410 nanometer, and you see that with increasing concentration with increasing the concentration of cadmium-2, you see it is just 1 micromolar, up to 1 micromolar the intensity has been increased a lot, okay, and it is excited at 410 nanometer. Okay. So, BTC 5N tetrapotassium salt can be used for cadmium-2 plus sensing. Okay. So, that means you see that using fluorescence spectroscopy we can also do the diagnosis with respect to this detection and at the same time maybe estimation of different ions in solution. Okay. Sodium plus sensitive, it is a very interesting case. It is benzofuran isothalate based system. The structure is like this. Okay. So, isothalate and benzofuran, and these two rings are connected by this crown ether like cavity containing 2 nitrogen over here, okay. And this is a cavity where your ion can enter into, okay, ion can enter into and get sensed. Now, the point is this crown ether like this cavity, they have very selective or very selectivity, high selectivity towards ion of appropriate size. If the size is bigger than this cavity size, then you do not expect to have any interaction, but this cavity size if bigger, if the cavity size is bigger than your ion concern, then ion will not fit in. So, there will be no interaction. So, interaction will only take place when the cavity size and ion size, these two match with each other. So, this is fluorescence excitation spectra monitored at 505. This is your fluorescence excitation spectra monitored at 505, okay, between 300 to 400, and emission which is excited at 340, okay, for this SBFI at pH 7 buffer containing 135 millimolar and 0 millimolar sodium plus. You see that there is an increase in excitation spectra also, but you see in case of fluorescence emission, you see that fluorescence emission is increased considerably. At the same time, there is a shift, there is a blue shift of the emission spectra. Okay. So, this is very sensitive to sodium. Now, that can be proved, because sodium and potassium, these are very similar. I mean, these are alkali metal ions. Okay. So, their properties are very similar. So, the point is potassium is bigger, okay, than sodium. So, if it is the size of the ion and the cavity size is a big concern, then we can think that there should be some characteristic change. So, for that you see that this is your SBFI. Now, this spectra is taken, okay. This is you see that the excitation spectra, you see let us go back to earlier slide. You see that excitation spectra is taken from 300 to 400 and emission is taken from say 350 to 650. Okay. So, your excitation spectra is from 300 to 400. You see that when we take excitation spectra, now excitation spectra, it is very characteristic of the system, and also it is sometimes it is very similar to your UV visible absorbance spectra. provided there is no complication within the system, then it will match very close with each other. You see that there are two things that is done. Emission monitored at 505. In this case, potassium ion concentration is 0, only sodium ion is varied. Okay, you see that it is increasing. Okay. And here what is happening, that we have added potassium from outside. Okay, we have added potassium from outside such that the total sodium plus K plus concentration being equal to 130 millimolar. Okay, and both are same scale. You see that here total Na plus and K plus concentration is 130 millimolar. What is happening, that here your K plus concentration is 135 millimolar and here sodium plus concentration is 135 millimolar. So, what is happening, you are filling up the difference between 0 and 135 by means of K plus in second case. Okay. That means, if it is a case of say 0 millimolar sodium, then in this particular case you will have 135 millimolar potassium plus, and here it is a case of 130 millimolar sodium plus, means there is no potassium plus, and you see the spectra are very close to each other. So, that means this particular system has got a huge selectivity for sodium ion. Okay. Similar to this SBFI, there is a potassium sensitive system like this. Only thing is that in case of SBFI, there were 3 oxygen atoms. I mean, this ring, it is what is the member, how many members are there? 1 2 3 4 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 member. This is 18 membered. What about the other one? Let us count 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. It is a 15 membered, and the other one is an 18 membered system. So, naturally, and other things are very similar to each other. So other thing you do not think about it, I mean, it is benzofuran isothalate. So, its cavity size is naturally bigger than the cavity size of the other one, SBFI. So, in this case, it is found to be selective to potassium ion. Okay, then the other one was found to be selective to sodium ion. Okay. So, what is the observation? Observation is that you do the similar kind of exercise, that here 0 to 135 millimolar potassium plus with sodium 0, and here 0 to 135 millimolar potassium plus, but the gap is filled up with sodium ion, so that the overall concentration is 135 millimolar. That means, for 0 potassium plus you have 130 millimolar sodium. So, you see that there are some changes. So, maybe some of the sodium ions are getting incorporated, but mostly potassium is more effective here than sodium. So, you see that PBFI and SBFI, these are more or less very selective to sodium and potassium ion respectively. So, such selective interaction, I mean this exploiting this particular concept, we can selectively sense this different ions. So, why this is happening? The thing is that this size is bigger, this size is smaller. So, sodium can fit in, here potassium can fit in, and therefore, you can expect to have a selective interaction with PBFI or SBFI. Okay. So, that is something, you know, these are the few examples that I am giving you over here in this particular lecture, to give you the idea that how this fluorescence technique can be utilized to find out, you know, or to identify some ions. So, in that case you need to think about some ion selective fluorophore, and of course, while doing that you should also check whether this particular ion selective probe has got or is prone to interfering other ions. So, that we also should check, but this fluorescence spectroscopy gives you an idea that how experimentally directly you can detect, and also in some cases you can quantify these ions in solution. So, this advent of fluorescence technique in solution chemistry has enabled people to you know to identify and to quantify, to estimate this various ions in solution, or maybe in vivo or in vitro in biological systems as well. Okay. Now, it is time to move to another interesting and important topic, which is called the chemiluminescence. Chemiluminescence means luminescence as a result of chemical reaction. Okay, as a result of chemical reaction. So, it is giving of light. So, it is called the chemiluminescence, chemical luminescence or chemical fluorescence. Okay. So, chemical reaction yields an electronically excited species that emits light as it returns to the ground state. So, that means while there is a chemical reaction, while there is some chemical reaction that is going on, that means there are some reactions in which you can generate excited molecule. Okay, and then while that excited molecule is coming back to the ground state, it emits radiation. Okay. So, electronically excited species emits light as it returns to the ground state and giving rise to chemiluminescence, and it is a relatively new field and few examples are there. So, you know, A plus B giving rise to C star. Okay, this C star, okay, giving rise to C and H nu. Okay. So, chemical system which is giving off light is chemiluminescence, and this chemiluminescent species can be used to diagnose many things. Okay. And one important example is luminol. Luminol is a very important chemical for forensic analysis, maybe analysis, I mean different forensic analysis involving blood, etc. So, this is very important. Luminol like systems, using luminol like system you can employ them in forensic and other applicative reasons. So, this is cyclic phthalic hydrazide. Okay. So, when you treat with oxygen and OH minus, then it is giving rise to N2. Okay. In alkaline condition, it is giving rise to you know H nu plus N2 plus water. Okay. And this is the characteristic fluorescence. Okay. It is the characteristic fluorescence whose maxima is around 450 nanometer. Okay. So, in biological system you can find similar examples. Okay. So, luciferase is a firefly enzyme. So, luciferin plus oxygen luciferase, in presence of luciferase, and of course ATP, I mean energy rich molecule and magnesium 2 plus, giving rise to this system, and then spontaneously it breaks to give you this light. Okay, and luciferin has got this particular structure. Now the mechanism goes like this. Okay, you see that this is your luciferin, D-luciferin, then ATP magnesium 2 plus, giving rise to luciferyl AMP plus PPI, and then it gives you H plus. Then in presence of oxygen, it is through these processes it is giving rise to a keto form and enolate form. So, keto form is giving you red light and enolate form is giving you yellow green light. So, this is the mechanism which is, I mean, this is the typical mechanism in biological luminescence or bioluminescence or biochemiluminescence. Okay. So, the idea is that you need to, I mean the process need to generate some electronically excited species, and that will undergo de-excitation, and at the same time it is giving rise to some radiation, means while coming back to the ground state it is giving off light. Okay. So, this is a important biological. Other examples, I mean that this chemiluminescence can be used to detect nitrogen monoxide. So, in presence of ozone it produces N2 star, and this N2 star NO2 star giving rise to this NO2, okay, NO2 plus H nu. Okay. So, its lambda is around 600 to 20, it is a broad spectrum. And also for the determination of sulfur, you can use this particular reaction, that is 4H2 plus 2SO2 giving rise to S2 star plus 4H2, and therefore H2, and then S2 star giving rise to S2 plus H nu. So, lambda is 384 and 394 nanometers. So, this way you can use this bioluminescence or maybe chemiluminescence for different purposes. Okay. So, that is why it has got application in various systems. Okay. Let us what is the use of bioluminescence or enzyme generated bioluminescence? You see that here it is also enzyme mediated bioluminescence. Okay. Enzyme mediated bioluminescence means you have luciferin plus O2, luciferase, ATP, Mg2 plus giving rise to light. So, it is enzyme generated bioluminescence. So, it is called the bioluminescence. So, it has got an application in bioluminescence resonance energy transfer. In this case, your donor is luciferase, okay, and acceptor is this GFP, green fluorescent protein. So, no excitation light source to excite the donor, which avoids problems such as light scattering, high background noise and direct acceptor excitation. So, in this way this bioluminescence has got some importance, that you do not need to use some light. So, enzyme generated bioluminescence you can use, maybe inside cell you can use it. So, it is in vivo monitoring of protein interaction. Okay. So, inside cell, okay, you can monitor protein. So, you need to have a source of radiation. So, where to get that source? So, if you have a source, suppose like a laser source, how to penetrate the light in your region of interest? So, in that case this can be useful, that your luciferase is the donor, acceptor is GFP, and then you are done. So, protein interactions such as this some clock protein insulin receptor activity, real time monitoring of intracellular ubiquitination, etc., etc. Okay. So, the firefly luciferin system, the best candidate for B rate based donor, and it has got the high quantum yield of, the quantum yield is very important. So, it has got a high quantum yield of about 88%, that means 0.88. Okay. So, this is very important. So, in this way your chemiluminescence has been very important in, especially in biological applications, where as I told you that light scattering has been avoided, then huge background noise. Okay. And so these are the things that we can find, that where we can find that this bioluminescence can be very useful. So this chemiluminescence or in turn bioluminescence can be useful for these diagnostics. Okay. So there are bioluminescent substances and enzymatic reaction of several common luciferases. Number one is aliphatic aldehyde substrate of bacterial luciferase. You see, this is one example, and it is giving 490 nanometer light. Okay. The second one is like this. This is luciferin, then ATP. Here actually in one first case aliphatic aldehyde, then FM NH2 bacterial luciferase, aliphatic carboxylate, and then FMN flavin mononucleotide, and then this is FMNH2 actually, and this is FMN, then 490 light. It gives you 560 light. Okay. And luciferin, then ATP firefly luciferase, it is giving oxyluciferin, then adenosine monophosphate, then PPI means pyrophosphate, and then light of generally 560 nanometer. Okay. And there is another example, coelenterazine. So, in using this reaction, it can give rise to light of 430 to 480 nanometer. So this bioluminescent substrates and different wavelengths, I mean, this is very useful because of the fact that you can also, depending on your requirement, you can also tune this light using different chemical reactions. Okay. And as a result of which you can probe different things. Okay. So that is why this bioluminescence is progressively becoming important, especially in vivo study, in vivo spectroscopic study. You can make use of this bioluminescence, okay, and bioluminescent substrates and also enzymatic reactions. Okay. Now, enzyme generated chemiluminescence, that is lumino-4 synthetic substrate that is excited through enzymatically cyclized reactions. You see, it is luminol, then horseradish peroxidase H2O2OH minus, this is giving rise to this, then N2 plus light. So, it is 425 nanometer, then acridan with H2O2, okay, with H2O2. Then giving rise to this acridone derivative, and then light of 530 nanometer. Then this adamantyl derivative alkaline phosphatase, then this is singlet excited, and then energy transfer giving rise to 480 and 530 nanometer. So, chemiluminescent substrates and enzymatic reactions of horseradish peroxidase and alkaline phosphatase is given here. So, this acridan also available as an ester like this, and then this is an important substrate as it is shown over here. So, you see that enzyme generated chemiluminescence and similar reactions are very important. As I told you that, like in application of this enzyme generated bioluminescence, you see that in vivo monitoring of different processes like this protein-protein interaction, etc., real time monitoring of intracellular processes. So that is why enzyme generated luminescence and enzyme generated chemiluminescence can be very important, okay, especially in this cell imaging maybe, or maybe especially looking for monitoring some processes that are occurring in vivo or inside the cell. Okay. So, in conclusion, what we have learnt over here in this particular piece of lecture, that we started with the discussion from metals that are influencing the chemical processes, this fluorescence processes. Okay. And in this line we discussed how phosphorescence, how in this line we discussed how metal ions can affect your fluorescence of fluorophore. It may be via quenching, which is called the fluorescence quenching, and this quenching, when there is it is a case of heavy metal, naturally it is the term spin orbit coupling comes into our mind. So, quenching by heavy metal primarily by spin orbit coupling. Okay. Next is we have discussed and given examples. We have given examples of different sensing systems with respect to metal ions, and we have discussed, we have given you the idea that maybe some of the species, some of these fluorophores are, not some, many of this type of fluorophores are very selective to some ions. Maybe someone is selective to cadmium 2+, someone is selective to say magnesium, like magnesium green, then fluoro 3, which is selective to another ion. Okay. So, calcium 2+ ion. So, these are by this particular discussion, here we talked about just I want to give you the idea that how fluorescence spectroscopy can be employed in not only in studying the chemical behavior of a fluorophore, like what is happening after photoexcitation, what is going to happen to these molecules after photoexcitation, whether some reaction is going to take place. Some reaction means maybe some excited state electron transfer, excited state proton transfer, or maybe some other process, maybe some real chemical reaction, or something else, like in applicative sense, whether this fluorescence can actually be used to used for some applicative reason, like in some application like determination or maybe identification or estimation of some metal ions. Okay. So, other side is means whatever we talked about before this is basically understanding of the behavior of an excited species or maybe behavior of a molecule after photoexcitation. And here employing this photoexcitation process, whether we can use this excited species to monitor some secondary, some other substance. Okay. So, I have not been able to give you more examples because of the shortage of time, but maybe if time permits, maybe towards the towards the later classes, maybe if time permits, then I can cite to you more examples, especially in this in the area of this sensing problem. And in the last part of this today's discussion, I talked about, I mean, just give you an just very short introduction of chemiluminescence and its possible application. Okay, especially the application what I talked about is this in vivo imaging and in vivo studies. This chemiluminescence is very important, and also chemiluminescence can be used to detect other substances like sulfur, maybe nitrogen oxides, etc., etc. So, that completes our discussion regarding this metal which is influencing fluorescence. This is one topic, and another is chemiluminescence. In the next lecture, we plan to talk on this solvent relaxation processes, that is solvation dynamics. Till then, have a nice time. Thank you.